Hey everybody, this is Paul Ian Kabasag. It's been a while since I did like a lecture video, but like a couple of my colleagues wanted me to revamp my channel here. So this is a comeback for me. I've just been doing just to give you guys background on what I've been doing. I've been doing a lot of just practicing engineering, structural engineering, fire protection engineering, electrical engineering, mechanical engineering. Yeah, just been doing a lot of the work, and then actually now I'm also a general contractor now, so I just do te technically the design and then also the construction. So yeah, mainly yeah. So if this kind of explains my background picture here. I know some of you guys have been asking what's the like background of this. So this was when I was working for Simpson Gupperts and Hager, but now I have my own company. Othno Design Realty. You guys have probably heard of it. Yeah, so our team here, we do a lot of residential and commercial work. So this new channel, I wanted to make it more driven towards practicing engineers. So I think the very best way I'm most familiar with, since I also have like I'm also a data scientist. I just finished that like a year ago. So I wanted to kind of mesh that together with engineering. So what I would like to, start with is I'm gonna give you guys a couple of lectures on the structural engineering codes. So the codes mainly is like ASCE 7. There's the California Building Code, NDS, National Design Code, and there's also the CE code, American Congress Society Institute. You also have the AISC code for steel, and then the AISI for cold form steel. So yeah, we're gonna cover a gamut of all the structural engineering codes, and I think this would help with everyone that's the designing buildings and bridges. It's mainly driven for the designing the structural engineering portion of it. So I think the most familiar code I would like to start with is the ASCE 7. So I'm gonna share my screen. If you hold for a bit. Okay, so here you go. So this is the code I was talking about. So this code is the one that a lot of structural engineers are using to get their loads. So the design loads come from this sole document, ASC 7, and I think now they have a more current version of this. But this is the one that I have online on a PDF. So I'm just gonna show you guys this. Of course, if you guys you could always use other versions, but this is the one that I'm most familiar with. So mainly that this ASCE 7 is this building code is called the minimum design loads and associated criteria for buildings and other structures. So this just wanted to cover what this is. So when it says minimum here, what this means is this isn't like the maximum or the only required. Any practicing engineer is gonna have to meet this or satisfy this minimum amount. You can't go less than this for like especially like earthquake loads and wind loads, lateral loads. But the main thing is these design loads are that have to be met before you can construct a building. So let's just cover maybe 1 or 2 chapters per session. And then and we'll see if I'm gonna try and make these videos maybe only like 30 minutes long. I'm not trying to, uh like spend so much time with it, but I would like to make it more continuous. So anyway, so let's just look at chapter, maybe the first chapter. All right, so it's chapter 1 here, is pretty basic. This one is going to be about like just a general aspect of the building code, just and then most of it is just definitions. Actually, before I even do that, let me show you guys the table of contents. So the table of contents, and the index is primarily your best friend when you're looking at these codes, especially when you're applying it doing it for a design project. For the most part, when you're designing something, like using inner calc or like RISA, a lot of these codes built in are already built in the programming. But then you still have to check whether your results are correct. So you always have to go back to this, especially for your loading combinations. So for when you're looking at this, um, the very first few chapters are pretty basic and they're general. That like we I just showed you, this is like mostly the definitions. And then you also and then the one I was alluding to is a combination of loads. So these load combinations are the ones that you have to watch out for, especially if you're doing ASD or LRFD. So ASD allowable uh, as strength design or LRFD load resisting factor design. So mainly when you're doing like wood design or like masonry design, you're gonna be using the ASD version. But if you're using like structured steel and I believe, yeah, and then ACI for concrete, you're going to be using LRFD load combinations. And this is where all engineers usually get their loading combinations from. So we're going to cover one and two, and then also the chapter three right here. It's pretty important. We're gonna have to. This is like one of the loads that everyone has to know. Obviously, is the dead loads. That's like the permanent loads in your building, all the building weights. And then soil loads. That's the loads on the ground. Mainly, this is you can also get it from the California Building Code, but the soil loads here is pretty much the California Building Code references ASC 7, I think now, instead of using two of the codes, they usually just refer to ASC 7 in the most recent code. And you also have this hydrostatic pressure load, which is just like if you have like saturated water or soil, it's going to create that water, that triangular distribution load. So, okay. So this is the table of contents. I'll always refer back to this before each lesson. So we're just going to cover chapter one, two, and three. So let's go to chapter one. Okay, so chapter one, pretty much like with every code, the chapter one always covers like a lot of definitions, as I mentioned. And you guys can read the scope here. Not mainly like if you're not familiar with any of the code design like this allowable stress design as I was telling you ASD that you can read the definition I mean for most engineers now they usually they're very familiar with the definitions anyways, but if there's one that you guys don't know, if you're still practicing or like I'm pretty new at it, you guys can always refer back to this. And so yeah, so chapter section 1.3 here has a strength and stiffness, and also have the performance base. I think the most important part I would say is just looking at I think this one has yeah, the risk category. So usually the ones that you use for design is this table 1.5-1. So this table 1.5-1 tells you the risk category of your building. So when you're trying to design a building, you need to know its occupancy. And its occupancy mainly if it's like in a residential or like a commercial or hospital and or like police station. Each particular occupancy of a building or use has a corresponding risk category. So for example, if you're doing the most typical risk category we use is risk category 2 right here. And this is the one that it says here all buildings and other structures except those listed in risk category 1, 3, and 4. So this is a catch-all, yeah, and all catch-all right here. So you can like anything that doesn't fall in like 1, 3, and 4. This is the one that people usually use. So like for example, like like a typical single family house or like an ADU. That's the ones that I get a lot of like clients for. Those ones mainly fall under risk category 2. And the higher the risk category, they go from 1 to 4. The higher the risk category, they the more severe the building loads are, because like these actually amp up your building loads so that it gives you more demand or more like conservatism in terms of applying it to the structure. And then, so for example, another example for what is a risk category one here is, so risk category one is like a very low risk. This is one where if the building were to like fail or like collapse, it's not really gonna cause anyone harm. I mean, so these are the buildings that's usually not occupied. Mainly, these are like kind of like barn houses, barn, like barn or agriculture buildings. And another, maybe one example I would like to talk about, because a lot of people ask about it, is what about for hospitals? Yeah, hospitals and like fire departments and police stations. Those are usually the high level emergency type buildings where during an earthquake or any type of like a storm event, you're gonna have to like you're gonna want those buildings to be operational. So that's why we want those loads to be higher. We want those buildings to resist higher loads. That's how you usually want to think about it. So the higher these loads are, the more like load demand. But at the same time, you have the capacity that of the structural members that you're trying to amp up the loads for to resist. So yeah, that's so these loads apply to all the loads, like flood loads, wind loads, rain loads, snow loads, earthquake loads, ice loads. And then it's very good to be as an engineer to be familiar with like, what each category what each building risk category are. And if you're not if there's one that's like more like a gray area, I would probably refer to the commentary. So a lot of these building codes, there's either in the end or right next to it if you're using a thing like the TMS masonry code or an ASCE concrete building code. Those ones will have it right next to side by side with the actual code and then the commentary. But then for this ASCE 7 code, it's mainly at the end. So if you guys look here, here, see, and then it's designated as C. It's one of the appendices, or after the after the appendices. So if you were to look here, let's see, let's look at this commentary for this section. So, all right, the yeah, this is on oh no, chapter one. We're in chapter one. Chapter one. If you look at the right functionality, risk category. Yeah, sure. Right here. So you have the basic stuff under here. Yeah, so you can read what each risk category are here. I think also in the actual code, they actually tell you what it is as well. So if you were to just read each one of these, um, see like here it says like other general protocol, which so they were still even like okay. All right, so that's pretty much chapter. I think chapter one has that one. I think that's the only one I wanted to cover with you guys, the risk category. That's the most important part of chapter one. But then now let's move on to chapter two. So chapter two here is this is the one this is probably one of the most important sections is the load combinations. So as I was saying to you earlier, it's going to depend if it's going to be a ASD design or an LRFD design, because depending on the material and then the philosophy of the ASD or LRFD, you're going to have different types of load combinations. So the load combinations mainly for like ASD design is actually in 2.4, but then the LRFD is in 2.3. So if you look at 2.4 first, This is the allowable stress design, and you're gonna see the main code load combination is right here. Meaning it's like 1 to 7. If you have like a dead load as your only like building load, uh, then that's the only one that you have to include in your like calculation. But then rarely like maybe risk category 1 will only have a dead load, but rarely do you ever find a building that will only have one load combination. For the most part, the most common one I would say is this the second one, the dead load plus the live load. So dead load plus live load is like probably like 99% of the time is the one load that you always use for like gravity vertical loads. And then when I'm talking about like, because a lot of people they always ask what is a dead load, what is a live load, and the main difference really is one of them is moving and the other one is not. So the dead load is something that's permanent. Like these are the building weights. Like this is like the self weight of your beams of your like columns. And like anything that's attached to it, like insulation or MEP that you do after a drywall. These are the ones that's usually permanent on your structure. But when we're talking about like people, a lot of times like furniture, people think furniture is a dead load, but it's really not because you usually move furniture around. Anything that's transient, though, that type of load falls on what we call a live load, an L load right here. So a live load is a load that usually that's moving and not permanent to the structure. So the dead load is a permanent load, while the live load is a temporary load. So when we're talking about like other loads, there's also not. I mean, this is I guess this is probably 99% of the time, but oftentimes you have other loads involved as well. You have the roof load, this LR load. You have this snow load, which is this S load. You have this rain load, the R load. And I think, oh yeah, you have the W load, which is the wind load. And then I think, yeah, that's it. And you have the wind load, yeah. I think that's pretty much it for the ASD. And then these different factors here, 0.75 or zero point 0.6, and then 1. These are different loading factors I was talking about. Is what you're gonna have to do is whatever load you have and that you think is gonna that structure member is gonna be subjected to either beam or column, you're gonna have to pick one of the ones that account that you think applies to your structure member, and then you have to pick the largest one. So when you're doing like structure analysis, where you find the largest load, usually you calculate each one, and once you calculate it, you find the largest one. When you do a hand calc, that's usually how you do it. When you're doing inner calc or like Reset 3D, all of this, usually you just apply the load, you draw the beam, apply the load, and then the computer usually just analyzes it for you, and then it picks the governing load. But it's always good to know where what the computer is doing. So that's what's mainly that's what's being done is the structure member that you have will have these different loads, self weight or superimpose, dead load, and then a live load, a roof live load. And then whatever extent of the loading, intensity you put in there, then then it's going to calculate the reactions for you. And whatever that reaction is it's already going to have that load accounted for. So mainly, so ASD. Let's say like we're gonna cover it more in like the NDS. That's the building code for wood, and then we're also gonna do like masonry design. That we're gonna be using this most mainly this loading combination for masonry and wood design. But the other type of load combination I wanted to cover is strength design or LRFD, load resistance factor design, which you're gonna find out that's another name for the strength design. So this type of load combination is mainly what is being used for structural steel and then with ASCE building code, as well as the ACI. That's the building code for concrete or reinforced concrete. So there's a difference between these two sections. So 2.3 here, 2.4 is the LRFD, 2.4 is the level stress design. So as you can see, it's pretty this one has like, let me see. So there's there's only five of these different ones for LRFD, but then there's seven here for ASD. And primarily when you're looking at this, you're gonna have to look at like like the loading factor. So if you, as you can see, like for the LRFD, mainly they try to bump up the loads. Well, that's one of the big differences. Except for this point 0.9 here and the point 0.5. But then for the ASD, mainly they try to maintain that load or reduce it. And essentially, the reasoning for that is because allowable stress design, it's a design philosophy where the maximum load that you're trying to get is just the and it is what you want in the end, but then you design everything less than that. But for the strength design, what you're trying to do is you're trying to increase its strength. So it's a strength, it's a strengthening factor. So that's let's take a look at the same thing as the LRFD ASD. So the LRFD here, for the dead load. This is like a very common factor, 1.4 dead. And usually you use this if there's no for a barn, like I said, or agriculture or building. If there's no one using there for typically you just use this. But then if it's a typical house or like ADU or any type of those type of buildings, typically you're gonna have people occupying that building. So that's why you're gonna be using this 1.2 dead and 1.6 live. So oh yeah, another thing I wanted to talk about here is there's also this or right. So when you see this point 0.5, you have like LR roof live load or snow load or rain load. What this means is like I said, you only apply these loads if you think that that type of load is gonna subject your structure, rather beam or column. So for example, if you don't have a snow load or a rain load, then you just use the roof live load here. What I typically do is I usually account for all of them and then I just pick the largest one. So for example, if you have like a snow load and a rain load and a rain load or like a roof load, because usually where the snow and the rain load are on the roof, is you just do point 0.5 roof live and then zero point 0.5 snow load and zero point 0.5 rain load, and you pick the smallest one. After that, then you add it to 1.2 dead and 1.6 live. So that's yeah, because usually you want to pick the largest one out of all this, right? Because this is a demand. So just pick the largest one and add it to the dead load and the live load. And yeah, oh yeah, I want to talk about this. Sometimes when people talk about this 1.2 dead and zero point 0.9 dead right here, but they have the same like a wind load. Usually this is for an uplift. So when you're using when you're trying to analyze an uplift scenario load case is you want to decrease your dead load so that you have a higher wind load because the dead load is counteracting the wind load here, right? Wind load uplift goes up and then dead load counteracts that with gravity going down. So that's why you have this point 0.9 dead right here. So in case that you have to account for because this one can actually govern or control depending on depending on the capacity or depending on the demand load of your wind. So yeah, that's mainly these are the two main sections, 2.3 and 2.4, that a lot of engineers typically use. And you're going to be referring to this a lot when you're doing your gravity design. There's also before actually I think yeah, we'll just end it with this chapter. We'll do chapter 3 and 4 next time, because those are the main ones, the dead and live load. So I wanted to cover. So when you're doing the design, typically you do gravity, and then you do lateral, and you do foundation. So gravity usually that's like a vertical type of load. And that's like a dead load, a live load, a roof live snow load, rain load, which is like the loads that you see here. But then the wind load, the W, and then also the E load, which I didn't really cover. Those types of loads are the lateral loads. So lateral loads, wind and seismic, those are like the two main types of loads that the E and the W that are part of the lateral system. So those types of the ones I covered are were mainly just for gravity. But when it comes to designing the lateral system, you also have to look at these other subsections right here. Because these other sections we'll talk about, you're gonna have other load combinations on top of the gravity for the seismic load especially. So right here, if you look at this particular one, 2.36, you're gonna see that like when you're doing the seismic load, you're gonna have the V and H, you're gonna have two different sections of it, right? And usually you're gonna have to compare both of these and look at which one is the largest one. So these two sections here are you're gonna have to add to your gravity load combination, and then look at whether which one is the one that has a higher dead load or like a total load. So mainly for seismic loads, yeah, it's kind of like same as when you're gonna have this like dead load that's reduced, because like seismic load, like what happens with that seismic load is you can go both ways because it's an inertial type of load, and so the it can have uplift, especially when you're doing like a shear wall. Shear wall has like those like overturning moments, and at the ends you have the boundary elements, and those boundary elements you have to consider uplift for when there's tension going up. And so this is the type of load that you're mostly gonna use to design your boundary elements. We'll get to the specifics of that once we get to the material building loads. Right now we're looking at the just the building load. ASCE 7. But once we get to like NDS, ASC, ACI, and TMS, those are going to become more familiar. And okay, well, if you guys have any questions about anything I just talked about today, this is just preliminary. I wanted to just give you guys a brief summary of the ASCE 7 and why it's being used, and then like the different definitions as well as like the loading combination, which is very important. And if you guys have any follow-up questions, just let me know later and I can answer that for you. All right, thank you. Have a good one. Bye.